Welcome to a curve sketching example. So in our example, we are to sketch the function f of x equals x cubed minus 3x squared minus 24x plus 9. We are to label all relative extrema and inflection points. So to sketch this graph, we need to find f prime, make the number line, find f double prime, make the number line, and then put it all together. So let's first essentially make the increasing, decreasing number line. So we know f of x is x cubed minus 3x squared minus 24x plus 9. So we have f prime of x by the power rule should be 3x squared minus 6x minus 24. We want to figure out where this is 0 or undefined. It's a polynomial, so it's never undefined. And if we solve the first one, we can go ahead and factor out a 3. We're looking at 3 times, in parentheses, x squared minus 2x minus 8 is equal to 0. X squared minus 2x minus 8, we can go ahead and factor. That's x plus 2 times x minus 4. So we now have either x plus 2 equals 0 or x minus 4 equals 0. And we get that x equals negative 2 or 4. We then create our number line. Our points of interest are at negative 2 and 4. This is x, and we have f prime, and then we'll have f up top. The derivative is equal to 0 at negative 2 and 4. Keep in mind that our derivative was 3 times x plus 2 times x minus 4. 3 is always positive. X plus 2 will switch at negative 2. And x minus 4 will switch at 4. So if we pick some point before negative 2, f prime, we have the 3 is positive. Then the x plus 2 term will be negative. If we're below negative 2, add 2, we wind up negative. And then x minus 4 term is also negative. So we wind up with a positive. We pick something between negative 2 and 4. That 3 is still positive. Then we are multiplying by x plus 2 has now switched to positive. X minus 4 will still be negative. It doesn't switch until we hit 4. So multiply these together, we're negative. And then for our last space, f prime, we're starting off with positive 3. Our x plus 2 is remaining positive, and now x minus 4 has switched to positive. Again, you could always just plug in a specific value, or you can just go by where each factor should switch signs and go from that. From here, we can figure out our function f. So f prime is positive, you know we're going up. You flatten out, go back down, flatten out, go back up. So already we know that our function has sort of a standard cubic shape to it, right? We could be precise and identify the relative maxima and relative minima. Identify the relative extrema. Well, we know based off of just our picture here, we know that at -2, we're going up and then turn around and back down. So we should have a relative max at -2. And the point would be at -2, whatever f of -2 is. Now we do technically have our function, so we could go ahead and simply evaluate that. Right? So our original function was x cubed minus 3x squared minus 24x plus 9. So f of -2 would be -2 cubed minus 3 times -2 squared minus 24 times -2 plus 9. And so that becomes, let's see, we'd have -8 minus 12 plus 48 plus 9. And we wind up getting 37. So our point, the relative max point, would be -2, 37. Next up, we had a relative min. At x equals 4. So the point would be at 4 and then f of 4. If we plug this in, we are looking at f of 4 would be 4 cubed minus 3 times 4 squared minus 24 times 4 plus 9, or 64 minus 48 minus 96 plus 9. And we wind up getting -71. So again, our relative min, the point corresponding to that, would be 4, -71. So we figured out not only the x value where these occur, but also just what the actual point would be. Now let's go ahead and do the number line for the second derivative. So let's find the number line for the second derivative, right, for the concavity. So again, we had the simplified form. We had f prime of x was 3x squared minus 6x minus 24 in the non-factored form. So we go for the second derivative, and we are looking at 6x minus 6. We want to figure out where this is equal to 0 or undefined. Again, we're dealing with polynomials. This is never undefined. And this winds up giving us that x is equal to 1. So if we draw our number line, the only point we're concerned about here is that x equals 1. Our second derivative was equal to 0. The second derivative, again, we're just looking at 6x minus 6, or 6 times x minus 1. So that 6 is always positive. And the x minus 1 will switch at x equals 1. If we pick anything less than 1, for example, 0, the second derivative, we're starting with positive 6 times, and then we'll have a negative. So the second derivative starts negative. And then once we go past 1, say x equals 2, we wind up with a positive times a positive. So we're positive. And our function f, we start off negative, we're unhappy. So it's frowning, we're concave down. Positive, we're now happy, it's concave up. And we will have a point of inflection, which I'm just going to label as PI for point of inflection. So we can go ahead and summarize this. We know we're concave down. Before x equals 1. Then we're concave up after x equals 1. And we know that we have a point of inflection. At x equals 1. And the actual point would be 1 comma f of 1. So if we look for f of 1, we're looking at 1 cubed minus 3 times 1 squared minus 24 times 1 plus 9. That's 1 minus 3 is negative 2, minus 24 is negative 26 plus 9. We would be looking at negative 17. So our point would be 1, negative 17. Now we can go ahead and put this all together. So if we scroll back up, we went down as far as negative 71 and up as far as 37, at least for the relative minimax. So let's just go counting by 20s. And then we only had to go out, let's just go by ones on the x-axis. So again, we just figured out that our point of inflection was at 1, negative 17. So this was our point of inflection. Our relative min was at 4, negative 71, and our max was at negative 237. So at negative 237 is our relative max. And then at 4, negative 71 is our relative min. So we know that we're starting off something like this. It's staying concave down until we cross through our point of inflection, at which point we switch to concave up. And then we have our min here. So this is a rough sketch. No guarantees it's accurate other than those 3 points, but we do have where it's increasing, decreasing, and where it changes concavity. Just a note, ultimately for curve sketching, I'm less concerned with your Y values than I am with your where it's increasing, decreasing, like at what X values things occur. So you don't have to find the explicit points, X value and Y value. I'm fine with you essentially not labeling the Y axis and just doing your sketch. It is good to know where one point is if you know it. In fact, technically our Y-intercept would have been at 9. So technically we should go through more here. But since I'm not being very exact, it's not going to be perfect, right? But this is sort of how we can go about sketching with the very precise points. Again, I'm perfectly fine with you essentially not labeling the Y-axis, not scaling the Y-axis, and just giving a sketch of here's where it should turn around, this is where it should change concavity. But you can be more precise with the Y values if we know the original function f. In our next examples, we are not going to know f, and so you won't be able to figure out the precise value.